Yeah, good morning, ladies and gentlemen. Let's begin our section. We begin the section. Let me introduce the Professor Chen Yuao. The Professor Yuao Chen received his master's degrees from USDC in 2004 and his doctorate from Heidelberg University in 2008. After spending several years as a postdoctoral research and project leader in Germany, Yuao was appointed as a professor at the USTC in 2011. His current research focuses on quantum simulation with ultra-cold atoms. He has also co-authored over 50 peer-reviewed published that have attracted over 4,000 citations. He has been awarded many prestigious prizes, including the 2013 Fresnel Prize for Fundamental Aspects from the EPS, the Qiushi Outstanding Young Scholar in China, the Tan Kan-Ki Young Scientist Award, and the 2016 Young Scientist Award for the Commission on AMO from the IUPAC. Let's welcome Professor Chen Yuao.
Okay, good morning, everyone. So, the presentation. Yes. Yeah, today it's great pleasure to have the opportunity that sharing you with what we are doing and what we can do in the future. And the title of my talk today is the practical quantum communication. I want to tell you how we did for quantum communication from intra-city to intercity, and eventually we aim to go global for practically. So, yeah, as a start, I would like to say that in like about 100,000 years ago, that Homo neanderthal and Homo, sorry, I couldn't pronounce the name well, but we know that. So, okay, the left guy is stronger, and they had even larger brain as even than ours, what we have now. But for right one, individually they are much weaker, but they developed the protopole symbol and the language. In the end, they win the battle and become now becoming the human now. And so this means the information exchange is very important during the human evolution. And of course, with the information exchange, then the most important thing is the information privacy. It still seems it's okay. So anyway, with what I want to say is that the privacy means the freedom of the thought, which makes the innovation and the social advancement. The social progress makes information more and more efficient. We know that start with that in beginning we send mails or post via horse, and then later we have the train and we have telephone. Nowadays we can really like FaceTime, we can face video chat within thousands or a few thousand kilometers. And what I would like to really to say is that the information exchange has been and will continually to be accomplished by the human evolution and social development. And the everlasting question is how to make the information exchange more efficient, which means computation power, and how to protect the privacy. And we know the challenges in the information security that nowadays we know there's backdoors in the chips, and also we know that the fibers under the sea before we consider to be very secure because there's no energy leaks out, but now we already have possibility to to really eavesdrop all the information through the fibers. We know that I mean, in some sense, it's the information leakage is, some sense, changed the result or whatever, or at least the rumors saying that. And recently, no, although it's okay, not really recently, it's like 2 years ago at the New York Times, the Google, Yahoo, and Yahoo claimed that the NSA stopped the communication without break into the data center, but just they eavesdrop the communication channel between the data centers. So actually, the information security is really a long-term goal. I mean, back to even 2,000 years ago, 400 BC, the ancient Greek, they already have the information encryption, that they put a paper on a stick and then write down in this way, and you will see that attack tomorrow, it's in some sense, it's protected. And if you bring the message and the stick individually, it's become more secure. And also, if the stick is not regular, it can be even better. And then in 50 BC, they already comes out not modern, a smart way by the Kaiser, and they basically they move the alphabet by 3 digits or 4 digits, let's say, which means the encrypt A by D, B by E, and also later in France it's even better, the Virginia cipher, which means which that you use a certain letter and repeated letter to encrypt it, which means like if you basically you for certain number you shift the alphabet by different numbers. And also in China we have also a interesting code. I mean, when they let's say there's a war that they have already encrypted with 40 different message for each one, like I want arrow, or I will there's no food left, I want the food for the horse, whatever. And before they go out, they will select a poem which has also 40 Chinese characters without any repetition. And now if they want to send a message, let's say this one, they will count. Okay, so for the ninth one, it's in Chinese character 5, and then they make the 5, get the stamps and send it out, and then it's a way for the encryption. But also then in the 20th century, the Switzerland has this ruler, and we know the most famous Angama machine, and in nowadays the data exchange, we need not only in the transfer, but also we need authorization that only authorized user can get it. We need encrypt the transmission. We need a digital signature that there's no change in the data. But all this encryption is based on the computational complexity. What it means? Which means, like the Kaiser's cipher, one can really crack it just we are varying the frequency of the letters which pops out. And also we know that Angama machine eventually was broken by the Turing's bombing machine, which leads really the win of the Second War. And we know that now the conventionally also let's say ISA 512 was cracked in 1999, 768 was cracked in 2009, and actually 2024 there was no report that it was cracked, but in the most secure place. Actually, I don't know. In all other countries like US, I believe, I mean, at least in China, in most secure places, they already start to use the 2048. They don't use the 1024 already. And we know that the pairing-based code cryptography, which is supposed to be the next generation, which was created in 2012, before it becomes the next generation. And also we know this year, February, Google announced that they corrected the SHA-1 protocol, which is for the authorization. Actually, so which means all these classical encryption methods that based on combination complexity can be correct in principle. So actually, so the encryption method we have now is actually not so much better than it has 2,000 years ago. It's just because there's no single or no smart enough person to find the algorithm to break it. And in 1841, there's a Palmer writes that human ingenuity cannot connect a cipher which human ingenuity cannot resolve, which is somehow not really true. So this is the information security, and then as I said, the computational power is also very important during the human resolution. So, but there's for the classic computation, there's a bottleneck that we know that for the Moore's law, which already standard for about 50 years, but now we know that it can be seen in the very near future that the size of the transistor will be becoming to nanometer regime, which one has to consider the once it reaches the atomic scale, one has to consider the quantum fluctuations. So the standard law will not work anymore. So what will be the computational power works? In the other sense, although we really, at now the big data, basically in a certain time, we create the data is more than the whole we have ever created. We still have a very limited computational power, which means the whole computational power in the whole world is about 2 times 20 to 90. What this means? Basically, if you have a password, you don't need it to be very complex. Only 0, 1. If you have this 90 digits, you take all the computer in the world. It takes about 1 year to crack your keys, your password. So interestingly, that the quantum physics that come after 1 century development come to give you ways that probably can be used to solve the bottleneck I have mentioned. So we know that the Planck, Einstein, Bohr, Schrödinger, Heisenberg, Dirac, they formed this quantum mechanics. And why Zuckerberg gives his baby for 1 month gift is quantum physics for baby. So that's that basically I want to tell you today. So the most key element for the quantum physics is the quantum superposition. So unlike the classical world, the person can be only here or there, which means when I stay here to give you a talk, I cannot make an experiment in the lab. But in quantum world, it can be in the superposition of the different places, which means I have one I can be a superposition that giving talk here and do some laboratory work. But I have to say, so this is not quite true that nobody can see me. So it's very, as long as any one of you look at me, I have only one place left. So that's the superposition of the quantum world. Just to make an example, let's say when I come back from Germany, so there's a quantum flight from Frankfurt to Shanghai. So there's 2 routines from Moscow and Singapore. If I go from Moscow, I will feel very cold. And if I go from Singapore, I will feel very warm. So then when I arrived, my friend picked me up. He asked me, so, hey, which way you go from? So I said, hey, sorry, I'm falling asleep, but I can check. So I feel my body, it feels like that I both cold and warm. So I told him that it seems that I took both routine. And he's very angry. He cannot believe that. So he told me, next time just stay awake, don't sleep. I said, okay. So I mean, I'm an experimentalist. I took 10,000 times of flight. I found that really 5,000. If I stay awake, say for 5,000, I feel cold. For 5,000 times, I feel warm. It really proves that I only take one routine. But this okay again. This example is not entirely true because not only me has to be falling asleep, but also the other flight other people in the flight, or like also the pilot. Also, I mean, basically the entire world has no way, or the entire world don't look at the flight. It will go both routine. But the message I want to give to you is that in quantum world, the state of the quantum object can be affected by the measurement. This is somehow philosophically is more, I mean, at least to me, seems more right. I mean, so for Newton's law, we know precisely predict every movement as long as you know the initial conditions. Does it mean that really implied determinism? For instance, the talk I'm giving today is it already determined from Big Bang? So I mean the efforts people working hard can they really, I mean, it's already determined, or it's possible, or it can really mean something. Fortunately, the quantum mechanics tells that the actions really can affect the world. So now, I mean, so that's the quantum superposition. When you put the superposition into the information, we get the quantum bits. Like it can be also for the quantum bit. For quantum, it can be photon, can be atom, can be molecular. For the classical bit, it can be 0 or 1. So you know, I mean, for the cat, it can be either alive or dead. But for quantum physics, it can be in the superposition of the alive and dead. So also the quantum flight I mentioned, experimentally we can really check that if you have the electron down here and you have two slides, and if you put something to look at the slide, which way it goes, you will find that each electron will pick one of the slides and one of the slit and left two shadow there. But if you don't look at it anyway, it will, for each electron, it will, so what left is the interference pattern like this. And this pattern can only happen that each electron goes from the two slits simultaneously. So in the physically, in entire my talk, so we will have the single photon for the used as the quantum bit. It will be encoded into the polarization. The horizontal means 0, vertical means 1. We have the arbitrary state of alpha h plus beta v, which means it's the polarization of the photons. We know that the light basically is electromagnetic field, so it can be polarized horizontally or vertically or 45 degrees. So the 45 degree basically means the superposition of horizontal and vertical. With this, superposition, there's a simple theory is that the unknown quantum state cannot be copied very precise. It's a very easy theory. So you assume that we have a copy machine. Classically, what we do, we have a letter, we scan it, and we print it to a blank paper, we get 2 copy out. So if we have also quantum cloning machine for quantum state, for the left one is the target qubit 0 or 1, the right one is the blank qubit. So what we want to have is 0, 0 to 0, 0, 1, 0 to 1, 1. But now if we put in, we know that a superposition state of 0 plus 1, what we have is 0 plus 1, 1, which is not correct, not what we need for the cloning machine. So this means that even a single qubit, a single unknown state, it cannot be copied precise. But what the hell is exactly the 0, 0 plus 1, 1 is it's a superposition to a multiple qubit. So which means it's this is what Einstein cannot believe for the entire of his life. So if these two cats stay at this kind of state, doesn't matter how far away one can be. One side of the Milky Way, the other is the other side. If you look at one of them, you see it's alive. You know that the other one is alive for sure. So this is Einstein called spooky action at a distance, because basically he believes as long as the distance is far enough, the measurement for one cat should not be affect the other one. So he claimed, he said that quantum mechanics is certainly imposing, but in his inner heart that the God will not play the dice. Of course, Bohr argued with him for almost 30 years, telling him that Einstein, you stop telling God what to do. But the nice thing is that such a philosophical argument finally end by Bohr's inequality, which can be examined by in the laboratory. So since actually 1970s, so until now, we are still take the experimental test, although it always proves that the quantum mechanics is right, but it still has some loopholes. So up to now, it's okay. I think people will get confused, but I think it's okay because, I mean, Niels Bohr says that anyone who is not shocked by quantum theories is not understanding it. And Feynman says, so I think I can safely say nobody understood the quantum mechanics. So after my talk, if you understand nothing, I think it's okay. But you say, I understand quantum mechanics, I think you didn't listen to my talk carefully. So, okay, but when we really, I mean, from the test of the spooky action distance, so, I mean, after the quantum mechanics has built up, so many people start to use that. Only like 10% of people try to really produce some manipulate the quantum state and to confirm that quantum mechanics is correct. They develop some technicals which now developed to quantum information processing science, which offers unconditionally secure way for quantum communication and powerful computational capacities. So what's the quantum communications? Why it can be secure? So as I said, so you see the photons, the single photon, first of all, it's single quantum, it cannot be cut. And there's some mistake. So it cannot be copied, as I said. So there's no cloning machine for it. So which means it's really unconditionally secure in principle. So any eavesdropping, if you want try to look at it, you will notice. And if you have the one-time pad encryption, it's algorithm free. So the one-time pad encryption is already proved by Xiaonon at 1949, and the security of the quantum key distribution was proved actually in this century. Also, there's another protocol in quantum communication called quantum interpretation. This is a way to transmit information from one particle to the other at a distant location without actually sending the particles. So it seems complicated, but actually it's not so difficult. If you want to transmit an initial state, we know that it cannot be copied. How we do? So we first share entanglement pair, then we perform a Bayer state measurement which projects the two states to one of the four Bayer states, which are maximum state I mentioned in previous slides, and it ends up with the state nothing but the initial state away from a unitary transformation. So once you know the Bayer state result, you do a unitary transformation, you get it out, you get the initial state. So here I must emphasize that without the Bayer state result by Alice, the state is still a mixed state. So the transmission of the quantum state will not be faster than the light, because we always need to wait for the result. So although it's although quantum interpretation was proposed for a transfer of the quantum state for communication, but it turns out it's also very useful. It's really an ingredient for also quantum computing, for instance, the distributed quantum network. And talking about quantum computing, it's really Yeah, sorry, it seems there's action left missing. Anyway, so for quantum parallelism, so imagine you have 10 bits. You have 1024 numbers. So you do any actions you have only to do it. Classically you have to do it one by one. But for quantum state, as I said, it can be a superposition of this 1024 state, which means you make a uniform transformation at this superposition state. It's equivalent to do 1024 actions in each each number. So this means it really can be exponentially speed up. So for instance, for the to factorize large number, basically, if I tell you that calculate 13 times 17, I think you can do it like in about 2 seconds. But if I can say how much, if 2030, like say 79, equal to which two number times up, it will take you quite a long time. So nowadays, all the RSA protocol basically is based on this computational complexity on this factorized big numbers. So if you have now, if you consider like 300 digits numbers for a classical terahertz computer, it takes 150,000 years to factorize. But if we have a quantum computer, terahertz quantum computer, it can take in a second. So also we have the algorithm for solving the linear equation. For instance, if we have linear equations with 10 to power of 24 variables, so with even the fastest supercomputer we have, the 100 petaflops, it takes 100 years. But again, if we are a computer with a terahertz, we can do it with 1% or 0.01 second. So, and also for another way of the power computation complexity showed up at the quantum simulation. Actually, when Feynman mentioned about quantum computers, he actually meant was the quantum simulation. The state of it was the initial idea is when you want to simulate the motion of the electrons, the most powerful supercomputer can do is about 40 or 45 electrons. I mean, nowadays we have the mobile phones can do with even 30. What does it take to simulate 300 electrons? The 2 times power to 300, which is already an estimated number of the known protons in the known universe. And okay, that's a brief introduction of the quantum information. So the first proof of concept demonstration of quantum key distribution was in 1992, and later it's go to longer distance. But actually, there's for realistic device there's some loopholes. For instance, because all this experiment was done with weakly coherent pulse. It's not really single photons. So there's a photon number splitting attack, and for the photon detectors, if there's an imperfection, there's also blinding attack. So basically, the single photon attack means so you have certain probabilities. Always have its Poissonian distribution. There's always certain probabilities. You have 2 photons, but the eavesdropper do is he block the single photons and keep one of the 2 photons and send the to the bulb at a no loss channel. So in this way, it can really but for the guys who communicate, they will think it's a channel loss. So nice. So because of the photon number splitting attack, all this the real secure distance of all this protocol, this experiment is about only 5 kilometers. In nicely 2005, there's a proposal comes out called decoy state method, which randomly pick up the intensities and to check whether if there's a eavesdrop in the channel, and so which leads to the experimentally the secure distance to exceed about 100 kilometers. And also for the photon numbers for the attack in the imperfect detectors, I will not go to the details, but we also now have the measurement device independent quantum key distribution, which is immune to any attack on detectors. So they can even give the detectors to the eavesdropper. So he can not he either allow us or not allow us to communicate. Once he allow us, he will not know anything what we communicate. So with all this, can we start to do one can try the really practically multiplanetary networks. I mean, we have the prototype of the networks so the first all-pass network is five nodes in Hefei, 2009. Then there's also in Europe, there's in Tokyo, and the first scaled multiplanetary network it was done in Hefei in 46 nodes. But the challenge to go to long distance is because the photon loss in fibers. I mean, I directly quote a sentence from this review paper that for 1,000 kilometers conventional fiber, even with the perfect single photon source, 10 gigahertz, and ideal detector, one can get 0.3 photon per century. So there are two main paths. One is satellite-based and quantum repeater. So for the first solution, quantum repeater, it's basically divided into a few segments. It first creates entanglement between distance and connected with entanglement swapping and purify, get high quality with purification. So actually the most important thing is the quantum memory, the storage and the retrieval efficiency to basically two key elements of this memory. So, but still, the quantum repeater is practically still a challenge. So, quantum repeater, which allows, it's similar as the MDI. So, it will allow you communicate or not allow you. But once it allow you, he will not. The repeater itself will not know anything of your keys. But so I mean, previously it's still like 2 orders of magnitude away to the line. This line showing the time of to create one key at the 500 kilometers. So last year we are finally able to go to here, which means at 500 kilometers you have really sufficient money. So it's really need a lot of money. You can get 2.2 hertz at 500 kilometers. So which means it's practically is really still a challenge for quantum repeater. But there's a alternative approach. So, you know, as classically, we cannot see the light here, so one can put something in middle, and it basically it can create the key with relay, and the relay encrypt the key with the other person. So send the key with the encrypted key created by this guy. So finally, it can get to the key. But in this method, the relay really knows everything, all the keys. So, but when we talk to the banks, actually in 2013, the banks come to us after we create the metropolitan network in Hefei. They come to us, so they are interested into the long distance. But we say, okay, the quantum repeater cannot really practically use, but we have this method. But they are getting very excited. They think. So initially we have the information can be leaked the entire line. Now it's really relaxed to a few certain points. So they really wanted to use that. So in fact, really encouraged by the users, we start to build the backbone. So, and of course the solution two is the satellite based, because we know that the vertical distance of the atmosphere is only about 10 kilometers. There's no decoherence outer space. So satellite will be an ideal platform to do that. So putting all this together, so we have a roadmap to large scale quantum communication. So we have the multiplanetary networks via fibers, intercity networks connected by quantum repeater or backbone, and a long distance communication between with the satellite. So so this is what we did basically. So in 2007, we extended the communication distance to 100 kilometers. We start to build up the network. we have the all-pass networks, and we start to build a metropolitan networks. Then actually another metropolitan network, these are two different ones. So for this one in Hefei, actually we run a lot of distributable tests. So basically now the networks, the devices are not really there anymore, because for the stability check, all the different, we put it to extreme conditions like 45 degree in the computer room, or cool down to like minus 10 degree, doing a lot of testing. And finally, we start this backbone project in 2014. So the backbone project, it has about 2,000 kilometers. So last year it was, end of last year it was finished. It has 31 fiber links, 32 trustable nodes. Why Beijing, Shanghai? If you look at it, of course, it has more than 1/3 of GDP and 1/4 of the population. So, and why pass through Hefei? Of course, because our university is there, so it has to go there. And so in September 29th, the backbone is succeeded, launched in Beijing. And if you look at now in 2017, the first experiment we are done is it takes entire table, and nowadays we have this 4U rack has capable for the 4-channel communications. The size is really decreased a lot, and the bit rate increased a lot. And this is some video for the applications. So this ICBC, it has a data center between Beijing and Shanghai. And initially, it's quite funny that actually the bank really needed the keys very eagerly, but in the key management in China, so sometimes they cannot get the seed key updated for more than a year. So ideally, not ideally, so initially they wanted to have at least once per half a year, but they cannot get it once a year. Now we can do it for 10 times per minute. And sorry, it's the data, it's in Chinese. And this is a application for the money transfer, and this is so this is application for the loop protection. Basically, if one breaks, if jobs there it breaks, it will automatically switch to the other loop. So with this backbone, then we have also quantum science satellite. Basically, there's several phases. So the first phase would be the possibility for a single photon really pass through the atmosphere. That was done in 2005. Actually, before that, when we proposed to do some satellite communication, quantum satellite communication, there are some. It was really declined. There's some experts really take out a pen, calculate that. Okay, imagine you have a 200 millimeter telescope on the satellite. After it passes to go to ground, the beam, because of the diffraction limit, the beam can already be about kilometers. You are not possible to do any single photon transmission. But not talking about if the coherence still arrive. So we really get some money from a grant, and to really did our very hard work. And finally, we first show that it can be still survive after passing through the atmosphere. Based on this experiment, actually, people are started to believe, and we started the key technology development project, which is phase 2, the feasibility for to develop basically the tracking device. For instance, you know that when the satellite move around, you have to really catch it. So the feasibility to do communication in high loss satellite ground channel, and then phase 3 will be overcome all the demanding conditions for ground satellite QKD. Finally, the satellite, the achieved key technology is actually, I want to mention that. So we have basically 2 really key technologies. One is the ultra high energy resolution, which can detect a single match fires light on the moon from the Earth. Also the angular spatial resolution is you can reading on the Earth license from at the Jupiter's orbit. So finally, it's launched last year, August 16th, and we have 3 missions of Matrices satellite. The first one is the quantum key distribution from the satellite to the ground station, and second is we have also entanglement in the satellite distributed to ground station, which is separable by 1,000 kilometers. Those spare tests prove that Einstein's still quantum mechanics is still right. And the last but not least is the teleportation from the ground station to the satellite. So all these 3 missions already done. And the next is the intercontinental quantum key distribution. Basically, use the satellite as a relay. When it passes through Beijing, create a key. Then basically the satellite around one orbit about 90 minutes. After a few cycles, I think it's 5 or 6 cycles, it will move to the Europe, and then it creates a key between the satellite and Vienna, and then use the satellite as the trustable relay. One can create quantum keys between Vienna and Beijing. So this was done also at when we launched the backbone, September 29th. We had a quantum-protected intercontinental video conference between Chinese Academy of Science and Austria Academy of Science. So basically, so this is at Vienna, and this side is in Beijing. So the video conference is protected by the quantum keys. So in the end of my talk, almost end, I would like to tell you a little bit what we'll do in the future. So first of all, of course, we have this quantum secure platform. I mean, we really right now we are use the data transmission. In the not near future, we want to really also the authorization and secure storage, and of course, in the future, we want to have at the mobile platform. So the customer can be really national, finance, government affairs, enterprise, personal use. And, in China, we always like to say something plus. So I want to also show you some outlook. So that if we have quantum plus communication networks, we have the private security, and we can also have quantum plus data networks. Basically, we can really have quantum protected, like say cloud service, smart cities, Internet of the Thing, or cyber systems. And I mean, we really want to have this quantum communication platform for all the different users. We want to secure every bit in the Internet. So this is a brief outlook. So we have the data center of the bank. We have really requirement. We have the data center built or planned for Ali, and also we have the supercomputer centers. And in the future, we want to really connect all of them. And actually, today they really are based on the backbone. They already launched another project which to go to the wide area quantum communication network. It was just approved yesterday, and today it was announced in the internet of our government. So, I mean, together with the satellite, we will also launch more satellites. We want to create the quantum satellite constellations. So we will really want to have the space ground integrated global quantum networks. We can have the infrastructure as a service to platform as a service or software as a service, and the quantum security. But actually, that's the practical side. But to me, or actually to the whole group, to the scientific group, we have the even more interested at the fundamentally. So now with the quantum satellites in hand, what we can do is we can really, there's some proposals to connect the relativities, general relativities to quantum physics. So that, for instance, the quantum gravity, you have say the Planck at the Planck scale, if you have it's not smooth anymore, time space, and even with the quantum science method says right now we already can perform the first experiment is the gravitational induced decoherential entanglement. So if you have if you have the gravitational induced coherence, it will look like the dash line here, but without it will be the solid line. So now the question is whether we are able to see this difference. This work is ongoing, and of course, as I said, it's all the Bayer test so far still has loopholes. So the most we believe the last loophole is the freedom of choice and the collapse locality loophole in the Bayer experiment. So what this means, this is saying that all the instruments or all the devices, when it's produced when it's manufactured, it's already, especially this quantum number generation, it's already there. Or also the detectors, when it records the result, it can cheat. So the solution is the human observer's experiment. So at least we believe that, as I said, we believe that when the talk I gave here is not already decided at the Big Bang. So with this human free choice, if we can really select the basis by the free will, we also can, if we also record the data really by human observers. For in some sense, actually in principle, even one can by human eyes, for instance, in the future. So but actually it's not really necessary you record by eyes, but you really need someone write down. Basically the collapse loophole tells you when it's really now there's argument going on. It's saying that when it's really when the state really collapses. So basically we believe that really so together with human conscious joined in the experiment, it can be. At least we believe that. If one saying that for the humans, it's not really, there's no free will, there's no any sense to any science, no. So of course one needs to at least to distribute the entanglement to light second at least. So we plan. I think it's about a 10 years project. So we will put entanglement at the Lagrange point and distribute the entanglement to the Moon and Earth, and to do this experiment. And in the end, we want to also put human observables in at least one side. So in the end, I would just take home message is that we will have the global quantum communication infrastructure, the quantum internet, the satellite constellate in the space, and the fiber network at the ground. And we will have we want to have the Bayer testing of human free conscious, and really test over the general gravities or quantum gravities and so on. So this is our team. Jianwei is the chief scientist for both quantum science satellite and the backbone project. Chen Zi is the chief engineer, and for the satellite, I am the chief engineer for the Beijing-Shanghai backbone. With this, I would like to thank you for your attention.
Thank you. Any question? Yeah, please.
As I understand the quantum network, you use entanglement to pass the key.
No. For the quantum network right now, we don't use entanglement. It's the decoy state BB84 single photon protocol.
The network does not use entanglement.
Not yet. Not yet. Okay. No. Yeah.
So basically, we're talking about
the single photon transmission. Yeah.
It's a quantum encryption network.
Yes.
Thank you.
Any question?
Yeah, thank you very much for your presentations. I'm Lee from IQ. I'm very happy to see this quantum-based computing is now applying to the real communication domains. I think it's one of the fundamental questions is how this quantum environment will mapping with or interoperable with existing computing environment. Like currently we are binary-based or computing capabilities are already implemented, used in communication environment. There's some of certain gaps between this binary-based and quantum-based. Do you have any little more explanation on how we are the combined of both two different spaces, something development of this interworking functions between two? Do you have something elaboration on that?
Yeah, and it's a very good question. Actually, for admin, I didn't have time to talk. So for the communication side, so the backbone we have, it's right now we use is the dark fibers. So we have the quantum state transfer. So the single photon really has the fibers which we use for the quantum channel is really do nothing but only the quantum stuff. And then we created the key, and the encrypted data was sending via the existing the data network, so the network. But actually already I think last year we already launched the new technologies which we use WDM, so the wave. We just need we can use combine everything into a single fiber. So start with the quantum key transmission, then also we need some key exchange for the privacy amplification. But this normally we do with another fiber for security reason. But also we can also put the encrypted data together into the single fiber. At 20 kilometers, we can do 5 terabyte encryptions. So this we can already do. So in the future, I think we don't need build additional fibers. We just use the existing fibers. You just give me some wavelengths region. I can put my quantum signal in. That's okay. So we really don't want to replace anything. And right now, as he said, so we only the so-called quantum communication is actually quantum key distribution network. Doesn't matter how it's called. This network aiming is create a secure keys only for the keys. Of course, we use it for the encrypted data transmission. But depends on the users. The users want to use their own data network before, it's also okay. If that's also one, you can use our bandwidth. That's also okay. And also for the quantum computing, I would say the same. So it can never be replaced anything. Now we have this laptop very nicely, but if you go to the supermarket, I think most of the ladies still use the calculators. It depends on the questions you are dealing with. So I think in the future it will be really a combination of the quantum and the classical at different layer, for instance.
Any questions?
Yeah, let me try to follow these questions. It looks now it's all this communication environment. The communication stakeholders try to adopt all this quantum computing, but mostly security aspect. That is one of the durable solutions, I believe. But still, we are concerned is one of our experts will start to look at apply of this quantum computing for security enhancement. But question is, this should be operated as a part of the overlay networks with existing communication environments.
Yes.
That would be something complexity between this interworking between this legacy existing infrastructures and the computing quantum computing based infrastructure for the security. So that would be raise some of the difficulties to apply of this quantum computing of the global infrastructure aspect. So I want to look at this, see how this is well fastly deployed with this quantum computing developments. And also, quantum computing is not only for the security aspect, will be in the future some support, as you can say, of this infrastructure as a service, platform as a service. What is the timeline or some development of this aspect? Can you share some little more details?
Okay, so for the timeline, I mean, for right now, of course, the first one can see is that, I mean, we last year the European flagship, quantum flagship commissions, they had a delegation with us. We discussed that. So one can, I think, in 10 years, at least, so the quantum key distribution can be used at least, probably not to use it, at least for these companies and the government affairs, which they really wanted to use that. I mean, we were within in next 2 or 3 years, or we will launch. Well, maybe let's say next 5 years, we will launch 3 to 5 more satellites still at the low orbit satellite for commercially for the banks abroad, also for the embassies, for instance, and also we will launch satellites to go to the Earth synchronized orbit, which means like 50,000 kilometers. Right now, this one is 500 kilometers. So but that's still for science satellite. And in the future, I think in 10 years, we have a few satellites at the Earth synchronized orbit. I mean, it's really, 3 satellites you can already see any point in the Earth. And so I believe in 10 years, at least, also for the people that personally, if you really want to use that, you can also use that. I mean, nowadays you need to charge your mobile phone every day, no? So I think in the future, besides charging mobile phone, you may also charge the quantum keys, and then you can use it during the day. That's for the quantum key distribution side. But already, I mean, especially these bank guys, they really think it's really, really crucial to distribute the keys. That's the only thing they really ask us. Don't do anything else. Just the focus on these things. It's already enough. It's really, and the remaining things they can do. But also, of course, all this based on. I mean, even we know that the competition, like also Google, also IBM, they start to compete for the quantum computing side. But for the quantum computing, I would say, in 10 years, what we will see is that at some certain problems, certain mathematical problems, we will show that the quantum can really do more powerful tasks than the classical, even than the supercomputer. But this mathematical problem might has no any applications. This could be so. Only certain mathematical problems, maybe useless mathematical problems, we will show that the advantage of quantums. But for really, let's say for a quantum computer which can factorize 300-digit number, this I would believe in at least 30 years, I think. But in between, there's another thing will happen is the quantum simulation. I think, for instance, like high temperature superconducting, I think with quantum simulation one can really have a method to understand that. That's something in between. That's I think.
Thank you. I think I'm beginning to understand. I'd just make a comment. In an early slide, you noted that social progress makes information transfer more efficient. In this audience, I suggest that the words be standards make information transfer more efficient.
Okay, yeah. Okay. Thank you.
Thank you. May I ask you a question? I think you said in your talk you said that the satellite has finished its 3 tasks. I'm very curious about how to testify the entanglement for the second task.
We really performed the Bayer inequality test. So we see it is, I think it violates the Bayer's inequality. So we get 2 points. So classically, the inequality cannot be more than 2. We have like 2.3 with like 4 or 5 standard deviations, something like that.
For the coincident, they must be at the simultaneously to get the.
No, we have the synchronized laser also. So besides the quantum signal, we have the time synchron. Exactly, we have the between the satellite and Earth, we can do the time synchronization at about I think 200 picoseconds. So it's really, that's also another, besides, that's also very, very crucial technologies. Before it's launched, I mean, basically, what we always argue that it's how good it can be. Besides the 2 I mentioned, that's, I think it's a very good question. It's really needed, not only this experiment, all the 3 experiments, they need the time synchronization to very nice, to a very good regime. Yes.
Another question is that I read your introduction about you do research on the key distribution. I just think that what is the feature of the key distribution? At this moment, you have said that we already have several key distribution protocol and the practical key distribution normally by the BB bus. But what is the feature about this? If we do the research on the key distribution, what we will do next?
Well, the research on the key distribution, what we've been do next, of course, I mean, one direction is also, the really device independent, for instance. For the device independent, in some sense, for practically, actually, the security is, it's very hard to understand, but the security actually not as good as the measurement device independent. But anyway, this I can discuss with you later. And also for another side, of course, I mean, help us to make the standard, for instance, we just had a project at the ISO for the quantum cryptography. Since I mean, this is one kind of now really I think one needed to make the standard for quantum computing, because right now it's really getting problem if the one people really want to use that. Especially like the banks. We want to have our network go to the bank computer center, and they say, okay, you must pass through some standard by the existing standard. But actually, the method they use to encrypt is way low than what we have. It's really, I mean, but they simply say, if you don't do that, you cannot go in. So that's very funny. I mean, for new things, it's very funny.
Okay, thank you. No, any questions? No questions? That's all. Thanks the speaker again. I think our talk, this section is over. Yes, thank you very much.
Thank you very much. So enjoy coffee break, and the last lecture session will start at 11. Thank you.
那我们就一条有4个人。
他们每次都是一个人，他们就是我们就直接给你。
这个就是我让那个学生就是负责他们这一条的人数，我到时候发那个就直接发给他。对，我这样可以。我先让他在到时候发给他，但是他不会。是给一个人吗？这条给一个人吗？对，这一排12人。哦，是给一个人吗？我让那个人数，然后让他发给这一排。不然太看一下。那就集体。那就这样，就是所有的给他，然后再按排数，然后你再发给其他负责人，可以吗？我后面会12，这个
Shall we begin our session 5? The topic of session 5 is advanced network infrastructure and architectures for data. So there are 4 papers in the sessions. Cover the different fields such as machine learnings and such and some physical security layers and visible light communications and trust management. So we will have our first papers speaker, Dr. Kumar. Yeah, welcome to give the presentations. Thank you.
Good morning to all of you. I am Nanjing Kumar, working in the Department of Information Technology, Anna University, Chennai. Today, me and Mr. Arun Raj will present our research work here. Our research work deals with applying machine learning technique to improve streaming video quality when last mile connectivity is achieved through 4G wireless networks. We implement our work on the top of HTTP for many reasons. First of all, if there is any existing standard on this, answer is yes. We have MPEG DAS used widely by video operators such as Netflix. What they do is they segment video, store at different quality rate, and based on the client request, it streams particular quality segments. This works up to some extent to stored video, but when it comes to live streaming video, it doesn't work as far as our experiment is concerned. Another issue is a lot of researchers have already worked on the way we are working it, but their focus is more towards predicting buffer occupancy. In other words, channel. Well, channel prediction rarely works in practice, we know, for many reasons. So when we say buffer occupancy, it also depends upon the arrival rate. In other words, channel condition. That becomes the difficult job. So what we thought is, let us do other way, instead of analyzing buffer or channel prediction, let us analyze the received quality at the receiver through the standard guidelines. In this aspect, we got ITU document which we treat as a reference, implemented as per their requirement. My presentation outlines includes very first slide. I'll talk about what is the main benefit of that going our approach. And our approach is based on client-server model for various regions. And then I'll be talking about a particular type of machine learning, which is called state action reward state action. We have used it here. And we embed ITU guideline or algorithm to evaluate quality at the client continuously. We'll present our experimental data, which we did on live streaming, followed by conclusion. Bitrate fluctuation over internet has many dimensions. We know that. It could be even policy of the internet service provider, it may be local government, it may be global ISP. But even if we agree that there is a sufficient net neutrality is there's no bias, still it varies because the underlying fund of internet is best effort service, which does not guarantee quality of service. In other words, bitrate. Things is still worse when the last mile connectivity is through wireless like 4G. This put together, we have a lot of difficulty in estimating bitrate, arrival bitrate and future bitrate. Solution, one easy solution could be change the underlying hardware software, but then that's not a prudent solution. What about migration to 5G? Well, a lot of expectation is there. We also hope we'll have better bitrate and we'll have at least bitrate guaranteed. But there was similar case when we were about to enter the 4G. But as of now, whatever 4G we have in my place, I comes to Chennai, India, we have did a lot of experiment measurement. Even 4G fails to meet our expectation. So the best solution always could be do something on the top of HTTP. Let the hardware underlying network behave the way it behaves. Let us do the content adaptation there. As you can see in the figure here, we need some mechanism to trigger some action at those peaks. Those peaks, we need not need to apply an advanced prediction mechanism, but estimate quality continuously. So those peaks, say the server, okay, take this action or leave this action. That's the main proposed work here. Well, we propose client and server, but client in our is not thick client. We don't say that there should be a desktop computer here. Client could be a thin client, but it should have capability to estimate bitrate and analyze the bitrate, say our algorithm, and then into report server continuously, periodically. This can be implemented still one process running at a server and process running at a client, and multi-threading communication concept can be applied here. This is what we did. So client has basically 3 threads, one thread for estimating bitrate, capturing packet into the job, another thread for estimating the quality, another thread for dispatching the feedback to the server periodically. Server could have 2 or 3 threads. The live streaming server has to capture from a hardware, basically a webcam, then receive the feedback from the client and adapt the ongoing session as per the client requirement. Basic process involved is here. The media capture, which is job of the server. It could be a live content or it could be from a database. Adaptation procedure, major part done by the client, which reports periodically to the server, but encoding and transcoding at many more times is the job of the server. Stream processing, server, service provider, and client all has some job as usual. Here we use no reference matrix ITU G.1070 to estimate quality. Basically, it was for video telephony, but our case we found that it could work, and that's the reason why we use that. And the machine learning technique we use is called state action reward, state action. In shortcut, we say SARSA approach. It is similar to Q-learning approach, but it differs a lot from Q-learning. First thing, it is basically online policy. It's not as Q-learning, we use exploitation, no, we call it exploration policy. Find the action and then calculate the reward. Unlike Q-learning, when the action depends on previous events. That's the main difference here. SARSA is well formulated, documented in many mathematical papers as well. This requires current state, current action, previous state, previous action, learning rate, here alpha, discount factor, and associated reward VQ. SARSA doesn't exactly define how to choose action, which sequence to choose action. For that purpose, we need a further policy. We define 2 policies, softmax policy and E-greedy policy. Softmax policy, we use Boltzmann distribution to choose the next action. Greedy policy was simple: choose a random action, find the associated reward, and do the job, and update the Q matrix. ITU G.107 documents such clear-cut definition, including mathematical explanation of the quality evaluation. It has two major components: Visual Mathematics IC and IT. IC represents the video quality resulting from coding distortion, and the second component IT is governed by what we call a degree of robustness due to packet loss. IC is more important to us because it is rated with the bit rate B, frame rate F, according to the set of equations listed here. And IT depends upon another set of two equations given here. This constant V1, V2, V6 up to V12, it is given in the ITU document. We have just taken those as it is and implemented this. Coming to our main proposed algorithm, which is exploration policy. The very first job algorithm starts from the capturing few packets, say 100 packets, and beginning we assign low learning rate around 10%, 0.1, and then around 50% discount factor, and the very first no reward. And then we estimated throughput based on the N 100 capture packet. Then from the streaming packets, we read the frames per second and the current resolution. We use this and use the equation 4 defined earlier to evaluate VQ. And Q matrix is updated every time, and current action is communicated to the server, which adopts the ongoing session. And this continues till streaming occurs. Next policy is relatively simpler to implement. Just choose a random action, find the associated reward for that, and do the job. We have another policy, and in this policy, with some probability, epsilon job is done here. Another policy is basically not our. It is based on a research paper published last year on IEEE transaction on consumer electronics by Mr. Martin. In fact, they had more complex parameters. They had 3 quality parameters. First quality parameter depends upon the bandwidth and buffer occupancy. Second parameter, they define terms of switching, R switch. Third parameter based on the video fridge. All put together, they said this is the total quality. This was updated on the well-known Q matrix. Well, we compare all these 3 implementation in our laboratory, and the result will be presented by my colleague, Mr. Arun Raj.
Good morning to one and all here. I am going to present the result and discussion of our research work. The proposed system was implemented during VLCJ framework, and the test parameters were chosen as per the ITU guidelines J.247 document. The experiment was conducted in laboratory environment, and video was streamed from the classroom setup. Then the various video quality parameters are such as PSNR, SSIM, and multi-scale SSIM, and 3 SSIM. In 3 you have the contains text, edge, and smooth regions, and VQM parameters. First we move to the PSNR. You see in the diagram, the proposed approach SQBA-SP achieves better PSNR, which is 8% higher than SQBA-GP technique and 5% higher than the QB-QA approach. Next, SSIM was observed and calculated for few selected frames. The proposed approach of SQBA-SP approach, and we observe the average of SSIM of 2%, then QBA, and 3% better than the SQBA approach, GP approach. MSIM multi-scale SSIM value was computed and analyzed by our experimental setup. The SQBA-SP approach algorithm produced an average of 1.2% and higher than the QBA and 2.2% more than that SQBA greedy policy algorithm. Next, VQM has observed and analyzed our experiment setup. In this VQM, you have many weighted parameters. Here, the higher value of video requirements, the maximum loss of the quality in the video, it go to the content, and lower value of the VQM is desirable. So we need to achieve the lower value. So in MSIM picture, our proposed approach produced 15% lower than the SQBA GP algorithm and 23% lesser than the QBQA approach. Next is 3SSIM. In 3SSIM, we have such as three contents as texture, edge, and smooth region of the video going to calculate. The proposed SBQA approach as 0.4% as more than the QBQA approach and 1.04% as higher than that SQBA and greedy policy approach. Next, we have calculated the inter-packet delay. One instance of inter-packet delay is analyzed for few frames as shown below. An average of 7.6 millisecond, an average of 7.6 millisecond is observed by the experimental setup. Next is this is the original video which we have taken from our classroom setup. First figure A is original live video of streaming. Second is decoded at the receiver side. Few frames for the original video during streaming was captured and decoded sequence as shown below in the figure for the differences. Since system has to monitor and maintain an average PSNR value of 38 decibel and SSIM index more than the point of 0.09 which we achieved, and this is a sequence which is less than the decoded sequence is not visible. You see the figure. Next, I move to the conclusion. On the implementing on the top of the HTTP was the last mile connectivity through 4G seamless environment in India. Then ITU TG 1070 model embedded in the algorithm of comparison of three algorithms. Then the SASA approach achieved the system goal, which obtained the appreciable. Then experiment conducted on live and stored video stream and resulted through various full reference metric parameters such as PSNR, SSIM, multi-scale SSIM, VQM, and 3SSIM. Then finally, implementation of multicasting service will require additional mechanism. In future, we will get to the migration of 5G networks. Thank you.
Okay, thank you. So I think they have to a very complex and very good jobs based on the machine learning and solve the problems of quite of a service in the 4G networks. So I think there is a lot of things to be discussed. Is there any comments or questions on their presentations? No? Yeah. Mr. Carl, yeah.
Thank you for the nice presentation. And machine learning is considered as a very important tool to solve lots of problems in telecommunication networks. One point I want to ask is, when we use machine learning mechanism and when we collect data from some point and do analysis in the other point, is it possible to do all the processing in real time, or how much latency occurs from probing to the processing and then making the decision and then acting or correcting the network. So have you done some evaluation, please?
Well, this is a complex task, and yes, it takes more time to execute that algorithm. But learning rate is where it decides how much machine has learned. It may be it has learned up to 50% or 90%. It takes time. That is true. But when we have to go higher adaptation, we need more intelligence. So this is the way to do it. Instead of spending more on channel prediction or buffer occupancy, better could be have a higher intelligence and do the job. So we need more intelligence. That's the reason we are looking for some well-defined model, and here fits the SARSA approach we discussed here.
Did you measure the latency that occurred from probing to the action?
We measure inter-packet arrival time, our previous packet, and we evaluated through full reference metric. Since we did laboratory, original video was available to us, decoded video is available, we just compare using full reference metrics like PSNR, SSIM, free SSIM, and so on.
Okay.
Thank you.
Is there any questions or comments on the presentations given by Dr. Kumar and the Dr. Arun Trust? Yeah. Thank you. Is there any questions? So I just have one question. It's about what can you done to simplify the machine learnings to support the quality of service? You just use some mechanisms by some feedback. So in my point of view, there should do some things with network performance measuring. If you do not measuring the performance of the network, how can you check or how can you identify the state of network? So I do not find ways you can sensing the network, the state of network. You only focus on the state of machine. So how can we connect the state of machine with the state of network? Please, yeah, thank you.
Thanks for asking this question. QoS at network layer, yes, that is a requirement, and we agree with that. But how is it on the top of HTTP? Our is more towards quality of experience. Once we're able to achieve more than 35 decibel in PSNR, more than 99 in SSIM, the decoded or streamed video is quite good. So very difficult to find noticeable difference in that. So we do not take care in this algorithm about the underlying layer QoS, but our leads to quality of experience, better experience, and validate through full reference metric. QoS part we are not taking care of this. We are leaving the underlying layer to take care of the QoS as per IPv6, whatever is available.
Only based
sometimes it may cause more delay, agree, but delay we are not taking care of this.
So your work do not based on the management of the network,
link level QoS,
not directed with the QoS, just based on some data captured before.
Estimate it, inform the center, change the system parameter, streaming parameter.
Okay. Is there any questions and comments? No? Thank you, Dr. Roma and Dr. Rogen. Yeah. So the next speaker, the next paper speakers is Dongzhou Wu from the North China Electric Power University, China. The title of the paper is Modeling and Analysis of the Spatial Inter-Symbol Interference for MIMO image sensors based visible light communications. Welcome. Ms. Wu, yeah.
Thank you for the introduction by Professor Shen. My name is Rongzhao Wu, and I work in the Yangzhou Intelligence and Electrical Institute, North China Electric Power University, as a research assistant. It's my honor to attend these well-organized and fruitful conferences and share the research on the advancing networks infrastructures of data. The topic of my presentation is modeling and analysis of spatial intersymbols interferences for MIMO image sensor-based visible light communication. Okay. At the beginning, I'd like to introduce image sensor-based visible light communication technology. For short, I will call it ISVLC. The ISVLC is a kind of the low-speed optical wireless communication technology that uses the LED light to transmit the digital signal. And the image sensor is used to capture the picture of LEDs. And the image processing algorithms are utilized to extract the data extract and recover the digital signal. And the data transmission rates of the ISVLCs range from several kbps and several megabps. And the ISVLC technologies plays an increasingly important role in 5G network. Firstly, as we can see in this figure, in the left figures, we can see that the visible light wavelength is an undifracted wavelength, and thus the ISVLC technologies save the radio frequency resources, which is limited use nowadays. And secondly, since the visible light wavelengths can be used without license, and both the LEDs and image sensors is widespread used, thus the ISVLC is flexible to network. And last but not least, the ISVLC technology is harmless to human health and safety, so that it can be applied in some special scenes, such as the ICUs of the hospitals and the mines. Applications of the ISVLCs includes indoor positioning, intelligent transportation system, machine-to-machine communications, and the Internet of Things. In order to improve the ISVLC system performances, multi-input and multi-output screens is proposed. This is the structure of the MIMO's image sensor-based visible light communication system. The LED area is used as the transmitter. These technologies improve the symbol transmission rate and decrease the bit error rates and can be effectively applied in indoor positioning. However, it's discovered that the MIMO's ISVLC system suffers from the spatial intersymbols interferences. For short, I will call it SISI. And SISI is an interference between different LED channels. And this is a designed LED area. And the right of it is a light intensity controls plot of the LED intensity. And the same colors represents the same light intensity. As we can see, the digital signal of channel ABC, that's a little hard to see, the ABC 3 point. The 3 channels, and their light intensities is these 3 channels represent the digital signal 0. However, their light intensity rise from each other because of the interferences from other LED channels. And the producer mechanisms of the SISI noise is the straight line of the imaging system. There is 3 reasons linked to the production of the straight line. First, the diffractions caused by the grating edge and grating slit takes place. And the second, the refractions takes place because the camera's lens is contaminated and the surface of the optical components is not flat. Third, the reflection takes place on the inner walls of the tube. The distribution model of the straight lines can be expressed as the point spread function. This is the imaging result of the three different lengths, as is shown on the right figure. And it's shown that a smaller theta values of the PSF functions leads to the narrowest distribution range of the straight line, and the pixel of the LED is more concentrated. And the as to the intensity of the straight line, we can model it as the function 1, the first function. And the channel model of the IS VLC system, we can assume that the output optical signal of the LED area is the matrix P, and the receive coverage signal of the image sensor is the matrix I, and it returns as the second function. And the X term is the light power to current converts coefficients. Considering that the channels as a line of size link, the MIMO channels gain matrix is composed of the link G, and SI gains S can be expressed as H equal G plus S, and the link gain matrix G is a diagonal matrix, and SI gain matrix is a matrix that the diagonal elements is zero. So that we can modeling the channel's characteristic. The LED's light radiations is from the Lamberting model, and thus the diagonal elements of G can be expressed, and of the diagonal elements of S and also can be written as the Sij, and is equal to the double integrals expression. And the spacing distance of two LED, adjacent LED, this is a very important factor that impact the SI intensity. And Rij pi represent the distance in the imaging plane, and the Rij is the real distance in the LED area, so that we can obtain the received current signals of the I channel. And this is a conduction of the received SI noise and the SNR and BER expression. And in this paper, I do some simulation about the SNRs and BER performances. As we can see in the right figures, there's two important factors to impact the system's performances. The first one is the focal length of the lens, and the second one is the distance between two adjacent LED in the LED area. And we can see that as the focal length increase, the communication distance of the systems increase as well, and the adjacent distance of two LED increase, and the system BER performances is increased too. And it's a worldwide notice that it's interesting to find out that there is a critical value of the communication distance. Once the distance is exceed this critical value, the BER performance of the system will decrease very, very sharply. As we can calculate the SI noise intensity, so that we can use this characteristic to to find out the optimal detection threshold. And the optimal detection threshold can be defined by finding the extreme values of that P. And the system straight lines produce the SI noise and the background noise component in the form of active noise. So we can act the free problems, and we can conduct our optimal threshold. The figures of the right shows that once we use the optimal detection threshold with the given SNR, the BR performances of the system will be improved. And the second figure shows that there is a optimal detection threshold is 6, and the optimal detection threshold is the threshold we conduct. And that's all my presentation, and thank you for your listening.
Thank you. Is there any questions or comments on Mr. Lee's presentation? Okay. Oh, yeah, Mr. Wu.
Thank you very much for very nice presentation and interesting subject. However, I have some question or the comment regarding the MIMO principle applied to the LED communication. Not MIMO is a very benefit for the gain for the radio wave communication. I understand, but for the LED communication case, the most cases should be a lower distance, like several meters, even 10 meters, 20 meters, so that in that case, the receiver of the LED communication become when using the MIMO, becoming the circuit will be complex. So that means the cost is high. So rather than to use the MIMO, but in case of the LED communication, we can select to the much more strong sending of the LED light rather than a very complex receiver for the terminal of the receiving side. So that is my observation. What is your opinion?
Thank you very much. Thank you for your question. And in my point of view, I think that though we use one image sensor in this system, but in the image processing algorithm, we subtract each LED channel to analyze individually. And the signal that transmit of each LED channel is different and individual from each other. So I think this is my comprehension of the MIMO's system in this system.
How about the cost? How about the cost of the MIMO? If you take the MIMO approach, they will spend more money, or they will cost high. So how to resolve the issues?
You mean the economies cost? Okay. In our real applications, such as in some supermarket or in here, and the MIMOs is the MIMO area, the LED area is a common use in this system. Yes, so that the MIMOs we have no need to transform them or change this screen, because the LED area is common use in our daily life. And the image sensor, as to the image sensor, as I said, one image sensor is enough. And in the image processing algorithm, we spread it to different channel. So the cost is no change. The cost will not increase. Okay.
So is there any question or comments for the Mr. Wu's presentation? No? I just have one question for you. Is there any considerations on the air quality if you use the light for the computation? Do you have some considerations about the quality of light, quality of air, such as fog and the air pollution? Do you have any ideas on how to cope with the quality of the air if you use the light for the communication? Yeah, thank you.
Thank you, Professor Shen. This is a very good question. And as this technology is an optical wireless communication technology, so the quality of the link is very important to the system performances. However, in the ISVLC communication, the application of this technology is more concentrated in the indoor screen, and so the air quality will be less considerate. And also I like to mention that in some applications that there is actually used ISVLC to realize the long distance communication, and in that system, the turbulence of the free space must be considered.
How long for the communications, indoor or the outdoor?
As I know, that's the longest communication distance is about 1 kilometer.
1 kilometer.
I read some papers about it.
Okay, thank you. Is there any questions? No? No? So, thank you, Mr. Wu. So we have a next paper from the Yuhan Jiang and Yulong Zhou, Nanjing University of Post and Telecommunications. The title of the paper is Secrecy, Energy Efficiency Optimization for Artificial Noise-Ended Physical Layer Security in Cognitive Radio Network. Welcome. Good job.
Thank you, Professor Sun. Good morning, everyone. My name is Yuhan Jiang. I'm from Nanjing University of Post and Telecommunications. Firstly, welcome to Nanjing and have a good time here. And then, I'm very honored to be here to join this conference. The topic of my presentation is Secrecy, Energy Efficiency Optimization for Artificial Noise-Aided Physical Layer Security in Cognitive Radio Networks. My presentation will include these 4 parts. First, a general framework of my research will be given. Second, I will present the system model for secure communications in cognitive radio networks and formulate a secrecy energy efficiency maximization problem. Next, an optimal solution to the formulated secrecy energy efficiency maximization problem, as well as the corresponding iterative algorithm will be presented. Finally, simulation results will be given to show the advantage of proposed security energy efficiency maximization scheme. From the picture, the network I researched was under 9 cognitive radio networks. In order to improve the secrecy energy efficiency of CRNS, we applied the artificial noise and zero forcing beamforming technologies. So a joint zero forcing beamforming and power allocation problem is formulated to maximize the SEE under the constraints of the total transmit power, the secret rate of cognitive user, and the quality of service requirement of primary user. However, the formulate problem is non-convex. As a consequence, we firstly transform the formulate optimization problem in function form into an equivalent one in subtractive form, and use the difference of two convex functions approximation means to obtain equivalent convex problem. As shown in the picture, we consider an underlying cognitive radio network where a cognitive base station with n antennas transmit a confidential message to a single antenna cognitive user in the presence of an immense drop with a single antenna. The CBS uses an isonance spectrum that is unoccupied by a PU to transmit confidential message. To improve the physical layer security of cognitive transmission, artificial noise singles are used to compose the ED. The SEE of interest in this paper is the ratio of the available secret rate to the total power consumption of the considered CRN. So we formulate an optimization problem to maximize SEE of the cognitive transmission under the constants of the SR of CU, the quality of service requirement of PU, and the total transmit power, namely this formula. Then the main work is to solve this SEE maximization problem. We design the normalized performing vector VC in the non-space of HP. Meanwhile, VZ is designed as a non-space of HP and HC to guarantee that the AN only decreases the channel condition of event drop. So the formulate SEE maximization problem can be simplified as this form. Combined with the objection function and the constant conditions, we can readily show the non-convexity due to its function form and logarithm function. It is thus challenging to solve a non-convex problem. We first transform the original problem into an equivalent one in subtractive form by using Dinkelbach's method. Next, we apply the difference of two convex function means to approximate the F2 PCPZ into an inner one. Assume PC bar is a feasible solution of F2 PCPZ. The first order Taylor series expansion of F2 PCPZ is given by the last formula. Then we can obtain the solution. Then we can obtain the optimal solution of a subtractive form. At last, it is clear that the problem is convex due to the fact that the object function is convex and all constraints are linear. Therefore, it is simple and straightforward to obtain the optimal solution to SEE maximization problem to using existing convex software tool. As shown in algorithm 1, a two-tier iterative power allocation algorithm is provided to obtain the optimal power allocation. For the considered SEE maximization problem, first of all, we initiate the maximal SEE eta SEE equals 0 based on the given eta SEE at the outer time. This approximation means it's applied to solve problem for achieving the optimal solution at the inner tier. When the view of F eta SE is updated for the next outer iteration. Meanwhile, eta SE is founded to satisfy the F eta SE equals 0 by using Dinkelbach's means at each iteration. When all the updated data nearly keeps unchanged or the number of iteration approaches to the maximization, the iteration stops. Otherwise, another round of iteration starts. Finally, we evaluate the performance of our proposed SEE maximization scheme through simulations. Our simulated results will average over 1,000 random channel realizations. This figure shows the SEE versus transmit power constant. As the transmit power increases, the average SEE performance of proposed SEE maximization and SR maximization screens all improve. This means that both SEE maximization and SR maximization screen can achieve the maximal SEE with the full transmit power. Then, as the transmit power continues to increase after 14 dBm, the average SEE performance of proposed SEE maximization screen approaches to a constant, while the SR maximization screen begins to degrade in terms of its SEE performance. Since the power allocator will not consume more transmit power when the maximal SEE has received. By constants, in order to achieve a higher SR, the SR maximization screen will continue to allocate more transmit power, which will result in reducing the average SEE. In addition, as observed, the proposed SEE maximization screen significantly outperforms the SEE maximization screen in terms of the average secrecy energy efficiency. This picture shows the SEE results versus the post SE maximization screen with the optimal power allocation and simple equal power allocation screens versus the transmit power constant. As we see, the proposed optimal power allocation significantly outperforms the equal power allocation in terms of the average secrecy energy efficiency due to the optimal of power allocation factor. That's all. Thank you for listening.
Okay, thank you. Thank you, Ms. Jiang. Is there any comments or questions on Ms. Jiang's presentation? No? I just give one comment. So I just review papers. I just want to know, could you give us some example for how to use your approach to solve some practical issues we have faced in the security layer, in the security or some other application domains? Could you give us some simple example to show the how to use your ideas or approach to improve our applications also? Do you have any ideas about how to use your proposal?
You mean that
how to use your method to some practical applications?
In fact, I researched this paper. I didn't consider the practical use. I only research here.
So based on your approach, which problems can be solved? Which technical issues can be solved within your domains, within your areas of do some researches? Is there any technical issues to be solved by such approach?
Oh, okay. My proposed screen can better balance the secrecy rate and the power consumption.
Okay. Only based on some criteria listed to lower error rate, to give some high security security guaranteed. Okay, thank you. Thank you. So the next papers presentators is a Yupo Jashinha. I do not know I can give correct pronunciations. And Professor Lee from the Liverpool John Moores University, UK. The paper title is Data-Centric Trust Evolution and Prediction Framework for the IoT. Welcome.
Thank you, Professor Shen. And my name is Supul Jai Singh, and from Liverpool John Moores University, United Kingdom. So our focus is mainly on establishing a trust framework for IoT and cyber physical systems. So, and also to collaborate with ITO on how to establish trust and especially standardization work. So here in this special session, I'll briefly explain about our research work on data-centric trust evaluation and prediction framework for Internet of Things. So here the main target is to have a platform to evaluate the trustworthiness of data. So basically, what is mean by trust? So you can see here, according to Oxford Dictionary, it says a firm belief in the reliability, truth, or ability of someone or something. So in simple terms, we can say if someone is trustworthy when he can do something that we ask, or when he's reliable, so or he's beneficial in some way that we can get something done from his collaboration. So in this kind of so this is the general meaning of trustworthiness. But when it comes to computer science, so how we can define trustworthiness? So in this regard, we came up with this definition of trust. So we can see in the screen is a qualitative or quantitative property of trustee measured by a truster as a belief in a subjective or objective manner for a given task in a specific context for a specific time period. So you can see there are a lot of properties that define trust when it comes to computer science, because like humans, the machines doesn't have a perception, so it doesn't have idea about the surroundings. So how to give this kind of intelligence to machines? So we should have this kind of properties defined when it comes to computer science. So also when we define trust, so we mean a relationship between two partners. So here we have two partners, truster and the trustee. Truster is who is evaluating the trust, and trustee is the one who is being evaluated. So basically, we say trust. That means the trustworthiness of this relationship between truster and the trustee, right? So with this understanding, so why we need trust in general? So there are a lot of problems. So when we use day-to-day applications, we get data from many unknown sources, right? And we don't know who is generating them in most of the time. So there are a lot of risks involved in using this kind of data. So in IoT, if we divide the IoT world into three parts, like cyber, physical, and social world, so there are unique threats in each layer. Like in cyber layer, we have malicious softwares, which try to get added advantage over other services, and physical devices there may be less sensitive devices, and there may be sensors who is vulnerable to environmental effects and so on. And in the social world, we have like malicious nodes which generate fake recommendations and so on. So how to tackle these issues when it comes to IoT? So using access control mechanisms, security mechanisms, obviously we cannot tackle these problems. So tackle problems of data integrity and these related problems. And other thing is, up to now, most of the research work has been done in regards to establishing trust of the end users or the end entities. But here, with our target is to find out the trust of data itself. So without considering the endpoints, so here we try to establish trust on the data itself without going for the end devices. So this is especially beneficial when we don't know, we don't have much information about the end devices to estimate the trust. So we propose four things here in this research work. The first thing is extend our research on entity-based trust towards the data-centric trust. So earlier we had proposed entity-based trust framework for IoT. Now we extend that work towards data-centric trust. Then based on combining these two frameworks, we develop a hybrid trust framework. We call it hybrid trust framework, so which can handle both entity-based trust and data-centric based trust. Then when we don't have previous encounters with other entities, so how we can evaluate the trust? So if I don't know about you, and then how we can predict the trust between you and me? So here I propose a trust prediction framework, prediction technique based on recommendations algorithms to predict the trust when we don't have previous encounters. And then finally, I'll explain these proposed algorithms in real implementation. And also here I have to mention about some of our standardization work. I think Dr. Kafil know much about this one. So my supervisor is Dr. Gayamulli from Liverpool John Moores. He's closely working with ITOT standardization group 13 and 20. So regarding the standardization group, study group 13, we have already submitted a technical report and recommendations on trust. So in these two reports, we have discussed how to establish trust. So primarily work on trust, like user cases, technical difficulties, technical challenges when it comes to trust provisioning in IoT. And under question 16, so we basically concentrate on knowledge-centric trustworthiness evaluation for networks and services. In this regard, we are still currently working on developing innovative solution for trust management for new services and business aspects. And recently, Dr. Gayamulli, he started this the second focus group about data processing and management. So under this one, I published this paper. So this is more related to this second collaboration. So which is about how we can find the trust, or we can combine the data quality and the trust. So in this regard, we basically consider data interoperability, classification, likewise these kind of issues in regard to data and the trustworthiness. So this is basically our standardization work. So in this standardization work and in the study group 13, we already submit this work, which is about REK model. So this REK model basically the fundamental model that we can calculate trust. So it has three trust matrices: knowledge, experience, and reputation. So we use these three matrices: knowledge, experience, and reputation to calculate trust in any IoT system. So knowledge represents like direct attributes that we can gather from other entities, and experience and reputation are like third-party properties that we have to that we can only obtain after some certain interactions. So after obtaining some measurements about knowledge, experience, and reputation of a particular system, so we can evaluate the trust based on these three properties. So this is the old model that we already published. So when it comes to this work, so we have a data trust model. So in this work, we extended our work like so initially we defined these attributes based on some end users. So we consider properties of end users to gather knowledge. So but in the data trust, we have to find the properties that defines the data quality. So in this regard, I choose these 6 properties: completeness, validity, accuracy, timeliness, consistency, and uniqueness. So if you search in the literature, you can find these properties, the work on these properties. So they have been extensively investigated about these 6 properties, and they have come up with the conclusion that these 6 properties define the data quality problems in general. So other than knowledge part, so experience, for experience, I use the properties like success and cost to evaluate experience, and the reputation is same like before. We use recommendations and rating from third-party partners. So using these attributes, so if we need to calculate knowledge, so we can combine this using a linear equation like here. So if we can combine completeness, uniqueness, timeliness, like in the linear equation, we can have the knowledge. Likewise, we can generate experience from success and cost, reputation from aggregating all the recommendations and rating. And finally, we can have the data trust value by combining all these knowledge, experience, and reputation. But the problem is how we can estimate these weighting factors. So it's not like a simple task. So you have to think about many properties of trust, and depending on the application also, these weighting factors can change. So in order to solve this problem, so in the one of the earlier publication of our group, we've come up with a proposal of how to use machine learning methods to combine these properties. So if you refer the reference 7 on my paper, so you can find that reference. So we use cluster-based machine learning mechanisms to find the trustworthiness of particular system and combine these properties without using manual method like mentioned here. So after you have these two models, so we came up with this trust framework. And so here you can see many components. So this is a generic model that we can apply for any IoT system. So we have trust computation, prediction, and decision making module. This is the main module that we are investigating now. Other than that, we have trust agents, trust data repository, API to connect to other services, and also trust service enabler. So you can see in the main platform, we have a trust metric extraction module. Inside this module, we have data-centric and entity-centric models. So based on the requirement, we can calculate the required trust based on the application. So here, so RK model, I use RK model for the trust evaluation because there are some other models as well. But in RK model, we have knowledge, experience, and reputation. So by calculating this knowledge, experience, and reputation based on these data-centric or entity-centric properties, we can have the trust values. So in order to calculate trust, we have several models like numerical model, machine learning model, and prediction model. So either using individual models or combining them all together, we can have trust computation. So after you calculate the trust, we have decision and delegation model. So it can use this trust value to take necessary actions. So the final thing of the proposal is like how to predict the trust when we don't have previous encounters. Right, so you can see here we have trusters U1 to NU, and we have trustees I1 to J. So you can say UN and I1 has previous encounters, so you can calculate the trust using this equation, final equation. But when it comes to U2 and I1, we don't have previous encounters. How do we estimate the trust between U2 and I1? Right. So in this case, we use the previously mentioned 6 properties: completeness, uniqueness, timeliness, validity, accuracy, and consistency. So these 6 properties can generate some information about the trustees, right? So using this feature vector and using the collaborative filtering method, we came up with this proposal. So if we can find some parameter that define the profile of each user, then if we multiply this parameter with the feature vector as mentioned in the equation, we can have some predicted trust value. So theta into trust feature vector, we can have predicted trust value. So how to calculate this parameter that define the profile of each user? So for that, we use mean square error method. That is the most common method available for in collaborative filtering. So here I compare the predicted trust value with the real trust value and take the difference. So the parameters that give the minimum difference will be the best parameter that describe these users. So using the gradient descent method, we can find these parameters. And after you find these parameters theta, we can multiply with the feature vector t. Then we can have some insight of about the trust between user and the unencountered trustee. So this is not 100% correct, but you can have some initiative based on this value, because without having any value, it's better to have some value to go with the future interactions. So using this, so next I will explain the proposal of our, so the implementation part of our work. So here I use air pollution and crowd sensing use case. So basically in the air pollution crowd sensing, we collect the data from various sensors like wearable sensors, moving vehicles, and fixed sensors, and store in maybe in a cloud, and analyze them in order to generate some meaningful results based about the air pollution. So here we propose a publish subscribe system. So any sensor who wants to send data, we can subscribe to our system and publish the data into our system, and any user who wants our data can subscribe to our system and get this data. So you can see this is a like centralized systems. I know that mostly we prefer for distributed systems, but here we have only considered about the centralized system. So if I explain the process very briefly, so when the new sensor comes into the play, so it has to register in our system. So after you register, it can send the data to our platform, trust computation, prediction, and decision making platform. So after it sends the data to our system, our framework can calculate the required attributes so that it can be used in a later time. So when the user requests any data from our platform, so our framework can find the relationship between the subscriber and the data that already received from the sensor, and it will come up with some trust value based on the previous suggestions and send this data towards the subscriber. So that's the basic or the simple idea about our system. And so basically, we propose in this work like how to extend our work on entity-based trust towards the data-centric trust evaluation framework and develop a hybrid framework, and also some implementation scenario based on publish subscribe architecture. But in the future, we have a lot of work to do. Actually, still this work is in the preliminary stage. So we are thinking about machine learning and deep learning techniques to evaluate trust, especially with the data trust, and also use some reinforcement techniques to improve the experience or the third-party attributes, calculation of accuracy of these third-party attributes, and improve the accuracy of trustworthiness calculation. Further, we hope to develop this framework about data-centric trust framework and have some standardization work published with the ITOT. So I hope you got some idea about our work, and if you have any question, please ask. Thank you.
Okay, thank you. Is there any questions or comments on Mr. Jachinka's presentation?
Yeah. Thank you for the presentation. I am here. This is a very challenging issue. We know that trust in data and to predict the trust when you have no pre-contact or previous knowledge. And yeah, we had one keynote speech 2 years ago by Professor Choi on this issue. And today you mentioned about lots of models and other things that you have been doing. I'm concerned with the results that you get. Results means when you predict some data to be trustworthy in some level, have you verified whether the prediction was 90% correct or 100% correct? I'm specifically asking you regarding the air pollution data, because you have been collecting data through the crowdsourcing, and then maybe you have to verify whether the data is trustworthy or not because it's from crowd. So have you done some experiments or anything?
Professor, this is like a position paper, so our idea is to give some insight about our research work here. So we haven't done any implementation in regard to a data-centric trust framework, but we have done like previous work on trust management and calculation. So in this regard, I use machine learning, and we found that it's pretty much accurate, because so we compare with the when we compare, first we calculate the trust using machine learning, then we compare with the successfulness of interactions between two parties. So we found that when the trustworthiness is high, we can see a lot of successful transaction between two parties. Something that kind of verification we have, but we haven't done extensive analysis on this research. So our idea is to give some our work on this project. That's all. Thank you.
It can answer your questions, or
I was looking for some verification data, but he said it's in the framework level now, and the data would be available later after doing experiments.
but to not give you a selected region, do not give the region how to evaluate the trust of the data by the 20, 80%, 100%. Do not give. Do you have any test or give some implementation method to predict, to verify the trust prediction? It have some variable if you give some predictions for the data trust in some value, in some regions, in some certain regions, you can see the data can be tested. Do you have make some tests or make some?
Yes, yes, we have done some trust computation in the previous paper. So we use a data set from the previous conference called SIGCOM, and they have like Bluetooth interactions between conference participants. So they have given like a mobile app, and they calculate. They get it's like a Facebook app. So they calculate. They get some information about some interaction, like who are their friends, who's mostly more involved with other partners, and some kind of social, like who are the friends of who what are the interesting areas of these researchers. Likewise, we had some like many properties about the conference participants. So based on this data, I came up with some numerical model that can calculate trust. So I published like it's like the name is how to calculate honesty of the honesty of the participants, something like that. So I use like some equations to assess the trust based on this data set. But other than that, I don't have much deeper analysis.
Okay, thank you. Any question or comment?
Thank you for your presentation. I'm trying to understand how I relate trust to security. Is security in the channel and trust in the node? Is there overlap? Could you comment?
There's some overlap, but basically trust comes to play when after you have like currently we have security mechanisms, right? So you have access control to the system. So you can log into some system using your security passwords and so on. But after you have logged into the system, so how we can ensure that you are trustworthy persons to this system? So that's where the trust comes into play. So right. So it's mostly about data quality, data integrity, how you interact with the system after you have gained the access to the system. So that's the area that we are thinking about.
And would I be right then in thinking of trust as a higher layer than security?
Yeah, it should be higher layer. So yeah.
So the trust is in the high level of the security, really?
Yeah. So inside the trust circle we have security. So I consider trust is the blueprint of all the things. So security is inside the trust.
Okay. So I think they are
so that means if
to the different domains. Belongs to the different domains. Security may have some different meanings. Trust is also have some their own meanings.
Yeah. So the basic idea is when we have trust, we don't have security mechanism. That was our ultimate goal. Yeah. Thank you.
Thank you. Is there any questions or comments? No, I just one questions. I just wonder how can you separate the data trust and the trust for some entity that that's related with the data. If there is no entity, how can we trust the data? The data should come from some entity. If you separate the data trust and the entity trust, I find that there's some confusion.
Yeah. So let's say we don't have identity about the device who is sending the data, right? So let's say maybe we have only a like IP address or something that, but we don't know much of information about this entity. But using these properties, like I mentioned, like 6 properties. So for any data stream, we can calculate these 6 properties like timeliness, validity, uniqueness, completeness. These 6 properties we can evaluate for any data stream, right? So we don't need to know about the entity itself. So entity has like different properties like willingness, disposition, like these common properties that define the entities. But in this case, we don't have to define the properties of entities, but itself instead of that we define the properties of data itself. So if we can measure the properties of data using these 6 properties, so we don't have to think about the properties of entity itself. So you got my idea?
So I just wonder, based on your some implementations, to sensing the air, sensing the quality of air.
Yeah.
So the data, how we can trust the data captured by the sensor? Is there any modifications? If the sensor get the data, someone may change the data, then upload such sensor data. How can we trust the data within the data center?
Yeah. In this kind of situation, where the experience and the reputation part is very important. So we measure the data now, and after 1 week, we see like some difference in the data set, right? Yeah. So, but we have some previous experience about this data set, right? So then we know that the previous data set and this one is different. So in this case, experience is different, right? So the experience is different means so there's something going on. So we can reduce the trustworthiness of this data.
Okay. Thank you. Any questions or comments? No? If no, the session is closed. Welcome to, thank you for all the speakers. Session closed.
Thank you so much for all the speakers. Now we're going to have, well, actually it's an early lunch, but we'll start at 2 with a tutorial with Beth Kaplan. Thank you.